Hey everyone, and welcome! So today, we are diving deep into the world of active filters. Now, if you've ever messed around with electronics, you know that filters are just essential. They're like the sieves of the circuit world. But as we're about to see, not all filters are created equal. We're going to find out how one single component can completely revolutionize how a filter works. So let's just kick things off with a big question. Why do those simple, basic filters, the ones we all learn about first, but just a resistor and a capacitor, why do they sometimes just fall short? You've probably been there, you design it, it seems to work, but it weakens your signal, or its performance completely changes the second you plug it into the next part of your circuit. It's a super common frustration, and it's the exact problem that active filters are here to solve.
And that really brings us to the two big families of filters. On one hand, you've got passive filters. They're simple for sure, but they come with some serious drawbacks. For one, they can't add any energy to the signal. In fact, they almost always weaken it, and their performance is totally dependent on what you connect them to. But then, you have active filters, and these are an absolute game changer. They can actually amplify signals, and they give you a level of design freedom that is just incredible.
Okay, so here's the game plan for this explainer. First, we'll cover the active advantage to see what really makes these things tick. Then we'll bridge the gap from theory to reality. After that, we'll get into sharpening the response by making our filters more powerful. Then we'll check out the expanded toolkit, and finally, we'll wrap it all up with the key takeaways. All right, let's jump into section 1, the active advantage. This is really the heart of it all. It's about how we can get total control over our circuits, specifically when it comes to amplifying signals and tweaking our design exactly how we want. So, what's the magic behind it all? What's the secret ingredient that makes a filter active? Well, it's this amazing little workhorse of a component, the operational amplifier, or as everyone calls it, the op-amp. Seriously, you can think of the op-amp as the engine that drives the whole filter, giving it superpowers that passive parts could only dream of. So let's put a pin in it. An active filter is simply a filter circuit built with an op-amp, some resistors, and some capacitors. And its whole job is to blow past the limits of passive filters. How? Well, it can provide amplification. It can actually boost your signal. And maybe even more importantly, it isolates the filter from whatever it's connected to. That means its performance is stable and predictable. And here it is, the single most important advantage. This is the power of independence. With an active filter, you get to decide exactly how much you want to amplify the signals you're keeping. That's the passband gain. And then you can separately and independently decide the exact cutoff frequency. With a passive filter, those two things are all tangled up. You change one, the other changes too. With an active filter, you are in the driver's seat. It's a whole new level of control. All right, so that control is awesome, but that leads us perfectly into our next section, from theory to reality. Because, let's be honest, having a perfect design on paper is one thing, but actually building it is a whole other story. Oh man, we have all been here. You've done the math, the equations all check out, and your filter design looks absolutely beautiful in your notebook. But then you look at the component values your math spit out. A 1 ohm resistor, a 1 farad capacitor. I mean, these are mathematically perfect, but you are never going to find those in a real parts bin. So, what do you do now? Well, the answer is this really elegant process called scaling. Scaling is basically the magic trick that lets us take those totally impractical textbook component values and transform them into real-world, practical parts you can actually buy, all without messing up the filter's performance. It is the essential bridge from theory to reality. And the best part? It's actually a pretty simple, two-step process. First, you do what's called magnitude scaling. This just adjusts the impedance of your parts to something reasonable, like turning that silly 1 ohm resistor into a nice standard 10,000 ohm one. Then you do frequency scaling. This is where you shift the filter's cutoff frequency from some theoretical number, like 1 radian per second, to the actual frequency you need, like 1 kilohertz. Easy as that. Okay, so now we know how to build a filter that actually works in the real world, but how do we make it perform even better? Well, that brings us right to section 3. Sharpening the response with higher order filters. In a perfect world, a filter would act like a literal brick wall. It would let every frequency we want pass through completely unharmed, and then, bam, it would instantly block every single frequency we don't want. Now, of course, a true brick wall filter is impossible, but how do we get as close as we can to that idea? The solution is actually surprisingly simple. We just increase the filter's order. And the way we do that is by cascading them, basically just connecting simple filters one after another in a chain. Each little filter stage builds on the one before it, making that cutoff sharper and sharper.
And you can really see the difference here. A simple first-order filter has a pretty gentle slope, or roll-off, between what it passes and what it blocks. But look at the higher-order filter. The roll-off is so much steeper. We are getting much, much closer to that ideal brick wall we were talking about. This quote just nails it. What it's really saying is that higher-order filters give you two huge benefits. First, a flatter passband, which means all the signals you want to keep are treated more equally. And second, a much steeper transition into the stop band, which means you're doing a way better job of rejecting all the noise and signals you don't want. This is the whole principle behind famous designs like Butterworth filters. So far, we've really only talked about low-pass and high-pass stuff. But the active approach opens up a whole new universe of possibilities. So welcome to Section 4, the expanded toolkit, where we look at band pass and band reject filters. See, with active filters, we can get super specific, creating filters that only pass or reject a very particular slice of frequencies. If you need a broadband response, to cover a wide range of frequencies, you can just cascade a simple low-pass and high-pass filter. But what if you need a really, really precise narrowband response? Something like zeroing in on a single radio station while ignoring everything else. Well, for that, you need specialized active circuits, and that's where they just blow everything else out of the water. Now, speaking of these specialized active circuits, there is one more absolutely massive advantage they have. It's an advantage that is truly the unsung hero of so much of modern electronic design. And here it is. With active filters, you can design almost any kind of filter response you want without using any inductors. Now, why is that a big deal? Well, inductors are often physically big, they're bulky, they're heavy, and they can be expensive. By using clever op-amp circuits instead, we can get the same results with just tiny resistors and capacitors. That means smaller circuits, lighter products, and often much cheaper devices. It is a huge, huge win. Okay, that brings us to the home stretch. Let's pull everything together, hit the highlights one last time, and look at the key takeaways that really show why active filters are such an indispensable tool for any electronics designer. I mean, this table really tells the whole story, doesn't it? Passive filters, no gain. Your design parameters are all tangled together, they're totally affected by their load, and they often force you to use those big inductors. But active filters, they can give you gain. They give you totally independent control over frequency and amplification. They're isolated from their load, and you get to ditch the inductors. It's really no contest. So, I want to leave you with this final thought. The real beauty of active filters is that they hand you this incredibly powerful toolkit built from just a few very common components. The design power is all yours. So the only question left is, knowing that, what are you going to build next?